right. Great. Well, it is my honor and privilege to introduce Leah Medeiros. She is a postdoc at the Institute for Advanced Study in Princeton, New Jersey. She is also a member of the EHT collaboration and a founder and also led their gravitational physics working group. She also led the EHT's testing gravity paper for the series of Sag A star papers that released in May of last year. So she will be sharing results from that paper with us today. Please welcome Dr. Leah Medeiros.
Thank you so much, Nicole. I am, sorry, I'm going to start my timer here so I can be respectful of all of your times. Thank you so much for that wonderful introduction. I'm so excited to be visiting Carnegie. I've never been here before, and I've already met several of you, and I'd love to chat some more with some of the rest of you if you would like for the rest of the day. As Nicole already said, I will be talking, at least the first half of my talk will be on some testing gravity results with the EHT. Before I move on from my title slide, I do want to tell you what it is that you're all staring at here. People have asked me if I'm trying to hypnotize my audience. I promise I'm not. I like my purple swirly. I think it's cute. But the real reason that I want to show it to you is that it really is, I think, the best visualization I have for what I think is the most gravitationally relevant feature in these images. So what is this? This is the result of a general relativistic magnetohydrodynamic simulation, or GR-MHD for short. What that simulation does is that we evolve matter as it swirls around the black hole. That matter gets very, very hot. It becomes a plasma, so then you just have a bunch of charged particles that are moving through the magnetic field of the black hole. They do interact with each other, and that causes magnetohydrodynamic turbulence, which is what causes the variability that you're seeing here. After we run the GR-MHD simulation, we also run a radiative ray tracing simulation, and that simulation calculates how this plasma would be emitting and how the emitted light would move through the curved spacetime of the black hole. This is actually a free color image, so everything that you see in blue is 1.3 millimeter wavelength radiation. That is the wavelength that the EHT currently observes at. And everything you see in green is 0.8 millimeter wavelength radiation, which is a wavelength that the EHT will observe at for the very first time in about 2 or 3 weeks. So obviously, I know that it's hard to see the green. Part of that is because this was done for media, and so I messed with the color scheme a little bit. But what you should know is that everything that you see in blue is really a bluish green, and they are practically coincident with each other, the 1.3 millimeters and the 0.8 millimeters. And everything you see in red is 3 millimeter wavelengths. The reason that this is important, that this is a free color image, is that you can hopefully see this very thin white ring here that remains completely stationary as everything else varies around it. That is the boundary of the black hole shadow. The fact that it is white shows us that it is achromatic, and the reason it's achromatic is because it is a gravitational lensing feature. The fact that it is stationary is also really important, as I will bring up later on in my talk. So whenever I'm talking about testing gravity with the EHT, I always like to be really clear about what it is that we, oh yes, please go ahead. Sped up by a lot. I think each frame is like 6 months or something like that for M87. It's, I can do this math. So this is, I think the actual thing is about 30 seconds. I'm not going to be able to do the math precisely, but it's really, really sped up to the point that like within a week, you really wouldn't expect to see any change for M87, or things would move like ever so slightly. Yeah. And the inclination angle is appropriate for M87 in this particular simulation. Okay, so as I was saying, whenever I talk about testing gravity with the EHT, I always like to be really clear about what it is that we are sensitive to and what it is that we're really not sensitive to. So in particular, I'm just going to focus on contrasting tests with black hole gravitational waves versus tests that we do with the EHT with black hole shadows. So when we are talking about tests with gravitational waves, we have a really dynamic space-time because you have these two black holes swirling around each other. Space-time changes dynamically. What that means in practice is that when you do a test of gravity with these sources, if there's any deviation from, let's say, Einstein's equations, we will notice that in those tests, right? So we're really testing the dynamical aspects of the theory. However, with the EHT, we're practically not sensitive at all to the dynamical aspects of the theory. The reason for that is that we have a supermassive black hole with a really small amount of mass swirling around it. So small, in fact, that we can effectively treat it as negligible, and we assume that the metric of the black hole is stationary as a function of time. So we treat this practically as a black hole that is not only stationary, but also in vacuum. And so we are really probing what the geometry of the black hole is itself, and we're really not sensitive at all to the dynamical aspects of the theory. So when I say I'm testing gravity, I am doing a metric test. What we're really testing is the no-Kerr theorem. So I want to know whether black holes in space are Kerr, and if we find that black holes in space are not Kerr, then it would really make us have to kind of look back at our understanding of gravity itself and black holes. Okay, so on my title slide, I pointed out that thin white ring, and that's the boundary of the black hole shadow. Here, I'm going to actually define what the black hole shadow is for you. In this diagram, this filled black disk here, this is the event horizon of this black hole. And this green circle is the photon orbit of this black hole. This is the radius at which it's possible for photons to orbit around a black hole. As I play the animation, you're going to see all of these lines are photons, and we're evolving the trajectory of these photons through the curved spacetime of the black hole. You'll see that all of the black photons will fall in, and sorry, not black, all the blue photons will fall in, and all of the red photons will escape to infinity. The boundary of the black hole shadow is given by the critical impact parameter between photons that fall in and photons that escape. We're going to zoom in now at that critical impact parameter, and you'll see that the photon that's right at that boundary is effectively tangent to the photon orbit. What that means in practice is that you can think of the black hole shadow as just a simple, critical impact parameter, mathematically perfectly fine. But if you prefer conceptually to think about it as the lensed photon orbit, you will arrive at the exact same solution, either definition that you prefer. And the radius of the black hole shadow as viewed by an observer at infinity is the square root of 27 GM over c squared. And you will arrive at that same solution regardless of which definition you prefer. Okay, so what I just showed you was for a Schwarzschild black hole, but of course we do expect that black holes in space will have spin. So the next obvious question for us to ask ourselves is how does spin affect the size and the shape of the black hole shadow? So this blue circle here, this is the boundary of a Schwarzschild black hole, of the black hole shadow for a Schwarzschild black hole. But as I play the animation, I'm going to increase the spin. Once it has a spin, it's going to be pointing up, and then you will all be observers at the equator. I'm going to go ahead and play that. You'll see that the shadow will move over to the right. But at least so far, the size and the shape really hasn't changed that much. It's only when we get to really high spins that we can create this deviation from circularity that you see here. Now, to our human eyes, we look at the shape and we instantly know that this is not a circle, right? But mathematically, if you actually measure the asymmetry of this shape, you'll find that it's actually really close to circular. What this means in practice is that the currently published EHT results do not have enough sensitivity or enough precision to detect a deviation from circularity at this level. So we cannot use this to constrain the spin of the black hole. So what about the size of the black hole shadow instead of the shape? Well, the radius for all black hole shadows for all inclinations and all black hole spins will always range between about 4.8 and 5.2 GM over c squared for a Kerr black hole. That's only about plus or minus 4%. And as you'll see throughout the rest of my talk, that's actually a really small error bar compared to what we currently have with the EHT. So you can be a pessimist or an optimist, right? So a pessimist would look at this and be like, wow, this is really terrible, because it means that we can't use the size and the shape of the black hole shadow to constrain the spin and the inclination angle of the black hole. The optimist, on the other hand, would look at this and say, wow, this is actually really wonderful, because it means that we can use the black hole shadow for this black hole to test whether or not this black hole is consistent with the Kerr prediction without having to worry about any free parameters, because spin really doesn't affect our measurement that much. So we're going to take the optimistic view for the rest of the talk today. But if you're interested in more about like kind of why this shadow moves and why it doesn't depend on spin, please do ask me, because there's a lot more to it that I'm just kind of skipping over here. Okay, so I've defined what the black hole shadow is in a way that only depends on the space-time geometry of the black hole and does not depend on any astrophysical effects. However, when we actually see the image that the EHT has published, that does depend on astrophysical effects. So we also need to ask ourselves, what is the relationship between this analytically defined black hole shadow feature and the actual observed ring of emission in the EHT image? So in both the first M87 publications, but also the Sgr A publications, we identified free conditions, and we argued that if these free conditions are met, then the observed ring of emission will be coincident with or close to this analytically defined feature. So first, we need to have enough photons to actually illuminate the black hole. Otherwise, we just won't see anything. Second, the emission has to originate close enough to the black hole so that it will be gravitationally lensed around it, but still primarily outside of the photon orbit. And finally, the surrounding plasma has to be sufficiently transparent at the wavelength that we are observing at. So in the top right here, this orange simulation, this is really meant to illustrate this third bullet point about the surrounding plasma being optically thin. What you're seeing right now is, again, result of a GRMHD plus radiative ray tracing simulation, but this is at a wavelength of 1 centimeter. At 1 centimeter, we can see these really kind of bright yellow features. These are the jets of the black hole. And this orange kind of fuzzy feature, this is the disk of the black hole. But we cannot see through the disk, and we cannot see the black hole shadow. What's really important to keep in mind here is that for both Sag A* and M87, these are both low luminosity AGN. What that means in practice is that the accretion rate is really low. Because the accretion rate is so low, they are radiatively inefficient, which means that they are not able to radiate away their heat. And so the disk will actually remain heated, which means that it will remain pressure supported and it will not settle down into a thin disk. So if you're used to like the alpha disk model, both of these black holes are not in that regime. What they will look like is more like something like this with this poofy disk like you see here. And so for these poofy disks, when we go to a shorter wavelength, we're going to go actually from 1 centimeter all the way down to 1.3 millimeters. You will see that the disk will become optically thin. We will be able to see through it all the way down to the black hole shadow feature there. It's really important to emphasize here that we didn't just get lucky. It's not that we just so happened to, stumble upon some black holes where these 3 bullet points were met, but rather a lot of theoretical work was done beforehand to predict at what wavelength these 3 bullet points would be met. So the reason that we observe at 1.3 millimeters and 0.8 millimeters is because of work like this, that as you can see, some of the actual citations that I'm using here are from quite some time ago, before we had actually built the EHT. Okay, we're going to focus now on the bottom of the slide here. This is another simulation. This is at 1.3 millimeters. This is only 1.3 millimeters, so this is not a free color image. This is just a color map. And the middle and rightmost panels are vertical and horizontal cross sections of the image on the left. In the cross section plots, I'm also including these vertical black dashed lines. These are the analytically calculated boundaries of the black hole shadow. First thing that I want to point out, there are these very thin, very bright spikes that are right at the boundaries of the black hole shadow. This is effectively that little thin white ring on my title slide. This is the photon orbit. You will find a lot of literature on the photon orbit and observing the photon orbit and so forth. But what I want you to know for this talk is that not a single one of my results or my claims are going to depend on actually detecting this feature in our data. And not only that, but none of the EHT endorsed papers depend on actually detecting this or claim to have detected this. The reason for that is that even though it's very bright, it's very, very thin. So if you take the integral of that, it's actually really small. And so in practice, it's actually a really small amount of the total flux that we observe. Not only that, the percentage of the total flux that we observe that actually comes from the photon ring is model dependent. So we really don't know how much of the flux that we observe comes from that. What I do claim, however, is that we observe this broader peak that you see here at the bottom. And I'm going to play this now, and you'll see that it is quite variable. But as you watch this, hopefully you can see that it's actually really hard for us to create a situation where we have a relatively thin ring of emission that is completely disjoint from the analytically calculated black hole shadow boundary. So if you have a ring of emission that has a width, effectively, it's very hard for us to create a self-consistent accretion model where that width is going to not contain this black hole shadow feature. Okay, so that was a little hand wavy, and I understand that. So for the testing gravity paper that I co-led with Maria Felicia De Laurentiis, we wanted to be a lot more quantitative and careful about this. And so we did a calibration between the black hole shadow and the emission ring in a reconstructed image. And the way that we did this was to break it up into what we call the theoretical uncertainty and the observational uncertainty. The theoretical uncertainty is defined as alpha 1, and that's the uncertainty between the analytically calculated black hole shadow feature and the size of the ring of emission in what I call the perfect image, which is just a high resolution simulated image. The observational uncertainty is the uncertainty between the perfect image and the ring in the actual observed image. What's kind of important to keep in mind here is that the way that we do this is with feature extraction algorithms that we apply to both the GRMHD simulations and the actual real image. So it's the exact same algorithm applied to both of them. And that is what gives us the width and the diameter of the ring. Okay, so this is the actual equation that we're using. You don't really need to remember this, but I'm going to go through it just in case you're interested. The measured ring diameter that we see in the image that comes out of the feature extraction algorithms is dm. The total calibration factor is just the multiplication of the theoretical and observational alpha-1 and alpha-2 uncertainties. 1 plus delta. Delta is the thing that we're actually trying to constrain. That's our actual final answer on what our precision is for our test of gravity, and that's what I'll be showing you later on. So this delta is what we use to constrain deviations from Kerr. And then finally, the diameter of the Schwarzschild black hole shadow is what we're comparing to. Okay, so for the theoretical uncertainty, in blue, we used literally hundreds of thousands of GRMHD images, all very high resolution, and they probe a really wide range of parameter space. And all of that is summarized in blue here, and this is the alpha-1 or theoretical uncertainty result. There are some assumptions that go into the GRMHD simulations, such as, for example, ideal MHD, which this is probably a collisionless plasma. So there is all kinds of issues with that, which I can get into if you're interested. So because of that, we also included a analytic accretion model, and that analytic accretion model was constructed in such a way to try to minimize the amount of assumptions that go into it. We try to just keep it to, like, some basic conservation laws and some pretty well understood and established plasma physics. And so hundreds of thousands of analytic Kerr images, and all of that is shown in orange. And then because we wanted to know whether this relationship would also hold for non-Kerr, we use the same analytic accretion model for hundreds of thousands of images that are with different spacetimes, and that is shown in green. The take-home message here is that pretty much no matter what we do, this relationship is really well behaved, really well understood, and it really seems to hold no matter what assumptions we kind of mess with here. But I should say the way that we do this analysis is that we do the entire analysis assuming each of these independently so that we have a final delta with each of these different alpha-1 calibrations, and you'll see at the end that they're all pretty consistent with each other. Okay, so for alpha-2 or observational uncertainty, the way that we did this was a completely blinded analysis. We only used about 150 synthetic data sets because it is a very human time-intensive analysis procedure. And so one team created these 150 synthetic data sets, shared that with the imaging and model fitting teams, and they did the full analysis the same way that they do for the actual real EHT data. The different colored histograms correspond to different imaging algorithms. You'll see that there is a little bit of a systematic between the different imaging algorithms that is completely taken into account in our procedure because we do the full analysis independently for each of them. But they're broadly consistent with each other, and this uncertainty is well behaved as well. Okay, so now we're finally going to shift onto the actual observations and the actual data. So the EHT is a very long baseline interferometer, and I'm going to give you a very brief intro to interferometry just in case it's been a while since you've seen it. So each pair of telescopes on Earth is called a baseline, and each pair of telescopes or each baseline will observe a specific location in Fourier space. So you take your two-dimensional image, you take a two-dimensional Fourier transform of that, and then each pixel in your Fourier transform is a complex number. And so each pair of telescopes or each baseline will observe effectively one complex number, which will tell you a little bit of information about the image. So the distance between your telescopes is what's going to determine the distance from the center of Fourier space that baseline is observing. The center of Fourier space will have information about low frequency components in the image, or in other words, it will tell you about the large scale structures in your image. As you move farther from the center of Fourier space, you will have higher and higher frequency, which will give you information about smaller and smaller scale structures in your image, or higher frequency Fourier transform, which will give you higher resolution in your actual image that you're reconstructing. What I really like about this is that we actually use the Earth itself as part of our instrument. So as the Earth rotates, each pair of telescopes will be at a slightly different location relative to the source on the sky. So each baseline will actually trace out these curves that you see here in Fourier space. And so these are the actual real observations that were carried out in 2017 for Sag A star. And these are the observations that were used to make the image that was published in May of last year. Okay, so this is the same thing that you just saw, but now I've added a legend. And on the right here is a very similar plot, but I've changed it up just a little bit. So the x-axis here is just the distance from the center of Fourier space. So these points, these blue points are the same here. And the y-axis is now the amplitude of the complex Fourier component. Now, for those of us in the EHT that have spent a really ridiculous amount of time, I think, staring at visibility amplitude or Fourier amplitude plots like this, we looked at this and we were absolutely thrilled because this is a Bessel function, right? So there's this very particular ringing feature here. And I've actually included this dashed gray curve here to kind of guide your eye. That dashed gray curve is a Bessel function for a very thin ring in image space. So Fourier transform of rings and disks are Bessel functions. And so for us, this already was super exciting. We're like, yep, this is a ring. This is amazing. So I want to spend just a little bit of time trying to build that same intuition and that same excitement that we had when we looked at the data for you guys. But I'm actually going to use the data from M87 because it's simpler. The reason for that is that Sagittarius A is variable on timescales shorter than the time that it takes us to actually collect our data. So we're going to kind of play around with the M87 data because M87 stood still for its portrait for us. So red data points are the M87 data. Yellow curve is the Fourier amplitude of this image here. And so is it possible to make a filled disk fit our data? I'm going to change the size of this, and you'll see that you are able to approximate the location of this first minimum, but you do a really terrible job with this second peak here, right? And also the location of where we think the second minimum should be is completely off. And so if I add a hole to the center of my disk, I do a much better job. Right now I'm approximating this height of the second peak pretty well. And also the location of the second minimum, or where we think the second minimum should be, is also pretty well approximated. If I blur it a little bit, the peak comes a little bit lower, which is a little bit of a better fit. And so, hopefully this builds some intuition for why we are so certain that it is not a filled disk. We do require a brightness depression at the center, and we are fairly confident in our measurement of the ring size, but of course there's an uncertainty on that. And so this is what the actual M87 image looks like. There is an asymmetry here, north-south asymmetry. And you can see that by the fact that this data point and these kind of 5 or 6 data points here do not fit the overly simplified image that I showed you earlier. And then for Sagittarius A, as I said, it is a little bit more complicated because the source is variable. It was much harder for us to just deal with trying to image the source. But we do trust that there is a brightness depression at the center of this image. And we do trust that we are able to measure a ring size with an uncertainty that I will show you shortly. But I do really caution you guys against interpreting the locations and the relative brightnesses of these little bright spots along the ring, because those really might just be artifacts from the imaging algorithms, but also from the fact that we just don't have that many telescopes. We need really tall mountains. So if anybody wants to give us tall mountains, by all means. But it's very hard to just be like, yes, I want a tall mountain in the middle of the Pacific. A little outside of our budget. Okay, so we apply the same feature extraction algorithms to these images. So there's one image that becomes really famous, but there's actually hundreds of thousands of images that we generate. And so these are the results of these feature extraction algorithms here, the mean diameters in micro arc seconds and the fractional widths. The 3 different imaging algorithms do have a bit of a systematic, but as I said, we take that into account. And these are the final results that we arrive at for this fractional deviation delta. This is really what we use for our tests of gravity. So the pink shaded region contains all of the different permutations of using, the analytic accretion with Kerr or non-Kerr, using the GRMHD, using each of the 3 different imaging algorithms, but also using the different mass over distance measurements as well. So we use the Keck results from the UCLA group, but we also use the VLTI results from the gravity collaboration as well. We do the full thing with each of those, and all of these different constraints, all of these different effectively posteriors on delta are all contained within this pink shaded region. And the blue shaded region is the prediction for Kerr that takes into account the fact that we don't know the spin and we don't know the inclination angle. So the first and most important result, yes, Einstein is still right. Nobody is really surprised, I don't think. We are consistent with Kerr. Sagittarius A is most likely a Kerr black hole. the next thing is, okay, what can we rule out with this, right? Like how strong really is this test? And so effectively, we have an error bar of about plus or minus 10%. When we compare that to what we had with M87, which is shown by this solid green curve here, what we had with M87 was about plus or minus 17%. So it's actually a lot better. But I just told you that Sag A* is variable, right? Sag A* is variable. It was harder for us to deal with. Why do we have a smaller error bar? Well, for one thing, Sag A* is a little bit bigger in the sky from our point of view. So it's a little easier for us to deal with from that perspective, but really it's a very small change. The main difference is the fact that we know the mass over distance so well. And to really emphasize that, for M87, before the EHT, we had two different mass measurements, one from stellar dynamics and one from gas dynamics. Stellar dynamics is shown in the solid and gas is shown in the dashed. Now, if you prefer the gas dynamics mass measurement, this would be a very different talk because I would be telling you that we've just proven Einstein wrong by order unity. So obviously we ascribe a negligible prior to that and we say, okay, there's some systematic that we don't understand about how we measure masses with gas dynamics, and the stellar dynamics is the correct one, and so M87 is still consistent with the predictions for Kerr. Okay, I also just wanted to show you visually what this 10% looks like on the actual image. Okay, so we can't use this 10% to rule out any parts of the parameter space for Kerr, but we can use it to rule out parts of parameter space for non-Kerr. So one of the things that I really enjoy to do is to take the Kerr metric and just kind of kick it and see what happens, right? So this is obviously way oversimplified. There's decades of literature that supports that very oversimplified statement that I just said, but there are metrics that have been developed that are parametrically that parametrically deviate away from Kerr. So these are just a couple examples of those. So this one is called the Johansen-Psaltis metric, or JP for short. And on the right, it's the modified gravity bumpy Kerr metric, or MGBK for short, and that's the metric of Visual, Eunice, and Stein. And these metrics are, developed with different choices, or some of them you can think of as effectively just you take Kerr and you add like a Taylor expansion to it. But there are different ways to do this. And there's also, GR is complicated. And so you end up messing things up a lot, right? So you might end up with like a metric where you can go in a circle and bump into yourself from 10 minutes ago. Pretty unlikely, but there's some issues, there's some nuances that go into this. But regardless, I like to simulate what the black hole shadows look like for these metrics. And so I have about 30,000 or so simulations of non-Kerr black hole shadows. And these are just a couple examples. And so I'm showing you the effect of changing the deviation parameter that has the largest effect on the overall size of the black hole shadow. And so what we can do is we can use these 30,000 or so simulations to place constraints on these deviation parameters for these parametrized metrics. I'm not going to go into too many details here, but effectively there's this hyperdimensional space, and I'm just showing you in the plots here on the right a couple cross sections of that. So on the top is a paper that came out in 2020 where we used my simulations to place constraints on this alpha 1 free parameter, which is the parameter that I'm changing in these different kind of rainbow colored black hole shadows here. And you can see that we can place order of a few constraints on these parameters. That's really like the take-home message, is that because we're in the strong field regime, we're really sensitive to deviations, even though our actual bound is only 10%, which seems like a huge error bound. We can actually place on the order of a few constraints on these different deviation parameters. So the top is for M87, paper from 2020, and the bottom is for Sag A*, the paper that came out in 2022. Okay, so for those of you who really have never heard about parametrized metrics before and really not the focus of your research, you might be wondering, okay, why should I care? What are we really constraining? What does this really mean in terms of other tests of gravity? So if you were to write your metric in a special coordinate system, which I'm not going to get into, but it's called aerial coordinates if you're interested, you can show that the radius of the photon orbit depends only on the time component of the metric. And since the black hole shadow is just the lensed photon orbit, you can therefore also show that the radius of the black hole shadow depends only on the time component of the metric. And again, if it's been a while since you've looked at GR, all you really need to know is the time component of the metric is the same part of the metric that we constrain with the precession of Mercury's orbit around the sun. And so we're constraining the same part of the metric. It's a very similar test that we're doing, but now we're in the strong field regime. And so the time component for a short trial metric, I'm just showing you an example here just so you kind of get a little bit of an idea of what we're talking about. But the take-home message here is that we can constrain the second order about 800 or so times better than what we can do with the best solar system tests that we have. So we're very, very sensitive to these deviations because we're dealing with black holes. We're in the strong field regime. So in addition to solar system tests, we also compare to what we can do with LIGO. And so these are some violin plots. And these two here are the best constraints that we have from LIGO and Virgo, at least when we published this paper in 2022. And Sgr and M87 here. So the really lightly shaded gray band is the prediction for GR, or specifically for Kerr, that takes into account the fact that we don't know spin. But what's really exciting is that if you compare the kind of the strength of the test, or how well we're constraining this posterior between the LIGO results and the Sgr results, it's really, really similar. So we're comparable in precision to what we can do with LIGO and Virgo. But remember, at the beginning, I mentioned that we're complementary to LIGO and Virgo because they are really testing the dynamics and we're really testing the metric. The other reason that we are complementary is the x-axis. So this is the mass of the black hole. We are probing almost 10 orders of magnitude in black hole mass, which is super exciting because we also like to look at plots like this, which show you the curvature, which I define here, and the gravitational potential, which I also define here, for pretty much every test of gravity that we could put onto this plot. So this, again, was something that we compiled for paper 6 for the testing gravity paper with Sgr. And so the point that I'm going to be talking about, as you know, is M87 and Sgr that live right here. But when you compare to LIGO and Virgo, the fact that all of these black holes are at such different masses means that we're probing a really, really vastly different curvature scale, which there's all kinds of reasons why you might want to know how gravity behaves at different curvature scales, which is why this is so exciting. Okay, checking my time. Okay, so I'm going to shift from testing gravity for a bit, and we're going to talk a little bit more about the future. So where do we go from here, right? So we have this 10% error bound. How do we improve upon this? What is going to be coming out of the EHT in the years to come? So everything we've published so far with the EHT is data that was observed in 2017. So it's been quite some time. Yes, it did take us forever. We understand. We are sorry about that. We're hoping to speed things up a bit. We've observed also in 2018, 2021, 2022, and we plan to observe in 2023 in, I think, like 2 weeks. Might be 3 weeks, so don't quote me on that, but 2 to 3 weeks. Since 2017, we've added 3 additional telescopes. So Kitt Peak, Greenland Telescope, and NOEMA all joined us for the 2022 observations and are planning to join us as well for 2023, which is super exciting. We also increased the bandwidth, which what this means in practice is that each little curve that you saw in 4A space is going to get a little bit bigger and also a little bit smaller. So effectively, we're observing at several different wavelengths that are really close together, so that each curve in 4A space is like much, much thicker, so we can fill it in a lot better. And finally, what is, I think, the most exciting is that we are planning to observe at 0.8 millimeters in 2023. The reason this is exciting is that the resolution that we will have will increase by that factor. So a shorter wavelength will give you an increase in the resolution by the wavelength that it is shorter. So it's, 1.3 to 0.8, not really a factor of 2, but if we are very optimistic, almost a factor of 2. And so our resolution should be improving by almost a factor of 2, which is super, super exciting. And again, this is happening in just a couple weeks. Okay, so in addition to all of this really, really exciting and really wonderful hardware improvements, software improvements a lot of times can give us just as big of an improvement or maybe even better. And so one of the things that I've gotten interested in the last couple of years is how can we use software improvements to improve upon this and kind of change the way that we have been dealing with interferometric data for the last few decades. So what I have done is a new algorithm called Primo, and this stands for Principal Component Interferometric Modeling. It's a machine learning algorithm. If you're in machine learning, it's really a dictionary learning algorithm, but funding agencies and other people really want me to call it machine learning. So it's machine learning in quotes. But the idea is that I generated a really, really large data set of simulations. We're zooming through it right now, and this is my training set. So I actually generated over 1 million high resolution images, but I ended up using a relatively small subset in like my final training set, but I kind of explored this full space while I was developing the algorithm. And so the way that this actually works in practice is that we have this space of images that you see here, and we can think about each of these images as a vector in this hyperdimensional space. Okay, so this is really just linear algebra. And so what you can do is that you can use principal component analysis to find a basis for this space. And I unfortunately can only draw in 3 dimensions. I cannot draw in 200 dimensions. So we're going to overly simplify it again. So these are the 3 main principal components for my vector space of images. And it's a basis that spans this space. And what we can do is that we can use this basis to approximate an example image. So here I have the example simulated image. I blur the image a little bit to approximate what would be like the absolute maximum EHT resolution over there. And what we can do is we can use a linear combination of those basis vectors to approximate that image. With free, we do a pretty terrible job. We get the basic thing, right, that this side is brighter than the other and so forth, but we're really not doing a great job. And so what if we use, let's say, 20? We do a much better job. Now we can actually approximate the fact that there is this little gap right here, which you can see right there. The fact that there's a little extended feature right there that matches that one right there. We're doing a much better job effectively. And so if you use 40, you do even better. Okay. And so the way that we actually implement this is as part of the MCMC algorithm. And so the MCMC will fit a linear combination of n PCA components to the data directly in Fourier space. I did prove that they do commute in a 2018 paper, and so that's important. So we do the PCA in image space, then we take the Fourier transform of the PCA components and fit those directly to the Fourier transform data. We also include an overall rescaling of all of the PCA components together, and that gives us the mass over distance. And we also include an overall rotation of all of the PCA components together, which gives us the orientation angle of the spin axis of the black hole. Now, why is this important and why does this work? So these are the baseline tracks in Fourier space for M87 from the 2017 data. There's a lot of empty space. We have no idea what is going on in all of these blank spots. Everything I've shown you so far and everything we've published so far, we need to have some sort of guess about what is going on in the places where we don't have data. And throughout, the last 20 years or so in the field of interferometric imaging, we've been using regularizers. So what do I mean by that? One example is that there are algorithms that try to reconstruct an image such that they fill in the regions where we don't have data by trying to minimize gradients in the image. So they're trying to create the smoothest possible image. If you're dealing with like a galaxy or something like that, that probably makes sense. But for black hole images, we know that there's a really sharp gradient, right, where we have that really sharp peak right at the boundary of the black hole shadow. So we know that that's not well motivated. There are also regularizers where you just try to maximize entropy. Why is that going to be the best for black hole images? We can argue about that, but I would probably be on the side that says it's probably not the best assumption for us to make. The list kind of goes on, right? So what we do with Primo is that we are actually learning the correlations between different regions of Fourier space. And you can actually prove analytically that the correlation length between different regions of Fourier space is about 2 gigalambda. What that looks like visually is like this. So each data point is now 2 gigalambda radius large. And so we're learning these correlations. And so we've effectively filled in almost all of the regions where we had the gaps in Fourier space. And so that's really what makes Primo so powerful. Okay, so we've applied this to some synthetic data. The original image here at the top, we've blurred that image with a 15 microarc second Gaussian filter, which is the size of the filter that was used for the currently published EHT images that I've been showing you. There's a whole other paper, which I'm going to skip due to time, that talks about why different filters give you different answers and kind of optimizes different blurring kernels. And so we use a Butterworth filter here. You can see already just using a Gaussian versus using a Butterworth filter, you do so much better with the Butterworth filter. The reason for this is that the Gaussian is actually suppressing about half of the power at baseline lengths between about 4 and 8 gigalambda, and we have data out to 8 gigalambda. So we're really kind of throwing out the baby with the bathwater, if you know what I mean, where we're really losing a lot of the data, a lot of the real power that we have by having these really long baselines by using the Gaussian filter that we've been using. And so anyways, at the top here is the result of a synthetic observation assuming the M87 baseline tracks with Primo, and this is the result that we have. And then here are the actual data points fit to the model that we have here. And so why is this better and what have we improved upon? Well, this image here comes from paper 4 from the M87 EHT publications. And in the top, we just have a uniform ring and then a fairly smooth uniform crescent. If we do a synthetic observation of these two images, these are the results that we get. So we create these little blobby features or these little knots effectively along the ring when we use these different imaging algorithms because of the regularizers that they have. You know, maximizing entropy or minimizing gradients will tend to create these kinds of features even if they are not really present in the original image. And so we're moving away from that so we don't have these little blobs or these little knots. So in addition to imaging algorithms, another way that we have tried to analyze our interferometric data in the past is with geometric model fitting. So as an example, we have a geometric model that is just a simple crescent. We can write it down analytically, and we just fit that crescent to the data in Fourier space. And so there's this whole other paper, which again, I don't really have time to get into, but I'm just going to really briefly summarize, where we looked at what the potential biases are of using models like that. Because when you have a simple crescent, you really don't have enough complexity in your model to really be able to accurately fit the data. And given that we have such sparse interferometric coverage, you can end up in a situation like the one I'm showing you here, where your original snapshot looks like this. This is what it looks like when you blur it. And this is what it looks like when you do a synthetic observation and try to fit it with a crescent. So you just fail miserably, right? And granted, this was a specifically bad example, and this is why it's my poster child of why this is a problem, is because it was pretty much the worst example we looked at. But there are several other examples that really, still do a pretty terrible job. And so you might say, okay, well, let's just add a little bit more complexity to our model. Instead of just a crescent, I'm going to do a crescent plus a Gaussian. Well, it does look a little bit better, but it's still pretty terrible fit, I would argue. And so we are able to fit effectively the same image, the exact same snapshot. I just rotated it for reasons that I can get into if you'd like. But we are able to actually fit the snapshot without the bias in the ring size that we see from these analytic crescent fits with Primo. Okay, the other reason that I'm so excited about this algorithm is that from the theoretical side, one of the things that we've been really struggling with for quite some time, and one of the main reasons why I actually was motivated to develop this in the first place, is the fact that we have this kind of like wealth of simulated images. But we're dealing with a turbulent system. So there's stochastic variability that's really hard to predict and really doesn't repeat, right? What does this mean in practice is that when you have a bunch of different realizations of turbulence, and then you have one other particular realization of turbulence, you can compare these different realizations with each other. There's no reason why they should ever match, right? There's no reason for you to expect that you'll be able to say, oh, hey, this image definitely comes from this set of model parameters, because you're looking at something that's really, really variable. And another way to think about this is that the level of variability in the morphological structure of the images is so large that the kind of space from each simulation, or the kind of breadth of the predictions from each set of model parameters, is broader than the difference between the different sets of model parameters. And so one of the ways that the Primos is really exciting is that it gives us a whole linear algebra kind of structure or infrastructure within which we can really do these comparisons in a statistical way, not just comparing one realization of turbulence to another, but actually comparing this kind of broader space of possibilities with each other. So if you're interested, I'd love to chat with you. Due to time, I'm going to gloss over some of the details and just give you an example, which I hope will kind of inform why this is so difficult. So all of these different little snapshot images that you see here, these are different realizations of turbulence. Almost all of them come from the same simulation. 2 of them do not. I'm going to give you 2 seconds to stare at this and try to guess which 2 do not match the others. Only one person has gotten this right, and to this day, I still don't know how she cheated, but I'm sure she did, because I can't do it. And I know what, like, I've seen the answer so many times, and every time I look at it, I forget. Okay, so these are the answers. Anybody get it right? Amazing, congratulations. Right? Anyways, so the point being that it's really hard to do these comparisons. Okay. So to kind of summarize what Primo does, it does not create the artifacts in the images that we've seen from the imaging algorithms. We are able to reconstruct more complicated source structure than the geometric model fits. We fill in Fourier space in a physically motivated way. I believe that this is the very first time that we have ever done analysis of interferometric data and filled in the gaps in Fourier space with machine learning in a physically motivated way. So that's really, really exciting. And I'm hopeful that kind of the broader interferometric imaging community will kind of catch on to this and maybe follow suit. So we are not limited to comparing specific realizations of turbulence with each other, but we can do this in a linear algebra sense of what kind of the vector space of the different images looks like. We can reconstruct images that are not contained in the original simulation data set. To prove that point, this is an example of a simulation where the spin of this black hole was 0.7. And I used a training set that only had spin 0.9 to do this analysis. And we do a pretty excellent job. So not only is that particular realization of turbulence not included in my training set, but the entire set of parameters is completely disjoint from my training set, and we're still able to reconstruct it really well. And this really just goes to show you that the actual breadth of the training set is really, really broad. And we have a really wide range of different image morphologies in the training set. And finally, this allows for comparisons with simulations to actually constrain model parameters in a much more physically motivated and in a way that takes into account the turbulent variability that we see in the simulations. Okay, can I keep going for a few more minutes? Because this is like the best part. And so I feel like if they suffered through the last 45 minutes. Okay, cool. So you might be wondering, have I applied this to real data? The answer to that question is yes. You might also be wondering, can I show you? Is it embargoed, right? It's actually not embargoed. Well, it's embargoed by me, but it's not embargoed by the collaboration because I am using data that has been public for over 2 years, which means that the rules change within the collaboration after 2 years. So I can write whatever paper I want and share it whenever I choose. Now, it is embargoed because I'm going to have a press release in about 2 weeks. So what I will ask of each and every one of you, including those of you on Zoom, please, is to not take a screenshot of your screen, to not take an image of this. Just wait 2 or 3 weeks. There will be a press release, and you are then more than welcome to do whatever you'd like with it. So this is the M87 image that we published in 2019. I use the exact same data set with Primo, and this is the image that we get. I'm affectionately calling it my skinny donut because I just think it's hilarious that it, sounds so unappetizing. Okay, so the ring size is actually completely consistent with previous results, which is great. So the mass of the black hole is probably consistent, but this current paper does not actually quote a new mass because I'm doing the full calibration with my algorithm now, and that's going to be at least a few more weeks. The ring width is smaller by about a factor of 2. We do believe that. And that's really, really exciting for a variety of reasons. One, it will help us constrain the parameter space for accretion models. So this will probably tell us that the accretion rate is really, really low. And that's how you create this really thin ring. The other thing that it'll tell us is that what we see is almost entirely a gravitational lensing feature, right? So I'm not claiming that I've observed the photon ring or that this is the photon ring, but you can probably argue that a higher percentage of the emission that we're seeing probably is strongly lensed than what we could have really argued realistically before, right? The other thing is that this brightness depression at the center is deeper and it is bigger. That's actually really exciting. There's a whole other section, or a couple sections in the testing gravity paper that I didn't have a chance to get into that talks about whether or not this thing has an event horizon, which is super exciting for the quantum gravity community, for example. One of the ways that we can constrain whether or not this has an event horizon is by the depth of this brightness depression at the center. So this would be super exciting for that side of testing gravity as well. Now, the little tiny tail at the bottom, do I believe that? Personally, I think that there's a pretty good chance that it's real. Am I comfortable claiming that and putting that in a paper? Really, I'm not. I think that what you should think about this is that this is just a hint of what's to come. I think that with 2022 data, we might really be able to constrain features like this, and we might even be able to see these features rotating around the black hole, which would be super exciting. But at least so far, it is possible for us to change the brightness of this feature that we see here and move it side to side ever so slightly, which I think in 2 slides, I'm going to show you an example of that. Okay, so I've also had some fun with this. So when the first M87 result came out, there were so many memes and so many things, right? And so in I'm really solving the world's most pressing problems by making sure that Homer Simpson is going to remain healthy for years to come with a skinnier donut. Yes, you have to have fun with your research as well, right? So this slide's been going around. Everybody in the EHG has been using this slide. I usually tend to not use this slide because I think it's too braggy, but I wanted to have fun with it. So this is like pretty much every major newspaper around the world the day after the M87 result came out. And so we can also make these a little skinnier as well. It's kind of fun. Okay. So because there is some machine learning in here, because of the way that we're doing this, there is a little bit of hyper resolution. I'm personally okay with that for myself, because I think that we have shown with a lot of different synthetic images that we are able to reconstruct features on this scale with Primo. If that makes you a little uncomfortable that there's a little bit of hyper resolution, that's totally okay. I also have a version where we have blurred it a little bit to suppress that hyper resolution. And this is what that looks like. And this is actually the version that's going to be the main version in the press release, because we're trying to be really, really conservative with the press release. But the other version is the one that I personally think is the real one. And that's the one, well, they're both in the paper itself. Okay. So when we compare the original M87 Primo and then a kind of blurred Primo, you can see that the little bit blurred Primo is still much, much, much better than what we had before with the previous imaging results. And this is what the actual fit to the data looks like as well. And talking about this little tail at the bottom here. So this is an MCMC, so I've picked randomly 3 different steps in the MCMC. All 3 steps are in the top 50th percentile of my MCMC chains. And you can see that it is possible for me to make this little feature really dim or really bright. And it's also possible for me to make this side, or I should say the relative brightness of this little feature and this little feature change. Obviously, 50th percentile is not the same as the absolute, highest likelihood, but it really kind of shows you the level of uncertainty that we have, which I think is really important to keep in mind, because this is still, not the same as you just taking a picture, right? But I also want to highlight that this is the level of uncertainty that we have with the other imaging algorithms. So even though there is some uncertainty, we're really, it's night and day compared to what we had before in terms of the level that we can really trust these features. And we're not creating these little, hot spots, which, by the way, when we made the synthetic data for that little ring, if you rotate the baseline tracks relative to the image, you rotate these little blobs as well. So they're really just artifacts due to the structure of the baseline tracks in Fourier space. And I can stop if you would like, or I can go through this slide and the next slide. There's 2 left. We're at 52, about. Okay, great. So I always like to highlight this because I feel like they really don't get enough love, okay? So I ask all of you to, also give some attention to the other black holes that the EHT observes. I have this image of like the Sarah McLachlan advertisement of, each year, other AGN are observed by the EHT, and they don't get press releases and nobody loves them. So we have images of other AGN. They are farther away, so we don't get that cute little donut, but we can see the actual jet. So for example, Sen A, this is my favorite. This is incredible. We are seeing the kind of the jet sheaf, right? The 2 edges of the jet for Sen A in incredible detail, right? We just published NREO 530 earlier this year, and I feel like nobody knows about it. So anyway, so there are all these other AGNs. And so what I wanted to do was also expand Primo to work with these AGNs in a model agnostic way. And so I did that with a student. And so Pravita Haller, this is her undergrad project, but she also did her master's thesis with me, and then she's now going off to grad school. I will miss her terribly. But she used effectively noise, right? So PCA, you'd never think to apply PCA to noise, right? Because you'd think that you can't do dimensionality reduction on noise. But if you actually were to do that exercise, if you create red noise images that have a particular power spectrum, this is an example of one of the red noise images she created. If you do PCA on let's say 10,000 of these images, this is the PCA basis that you're left with. There are some really interesting patterns here. It's almost like a Legendre polynomial basis. And so you can use this basis that's completely model agnostic to reconstruct images. And so the example here is kind of meant to approximate the kinds of features we see in 3C279. These are just a couple Gaussians, but if we actually do a reconstruction with her basis, we do a pretty good job with it. And what's also kind of fun with this is that within VLBI, we affectionately call what we do blobology, because everything kind of looks like blobbies, which beautiful, amazing blobbies, but blobbies nonetheless. And so what we kind of jokingly or affectionately call this project is that we made a blobby basis for our blobby VLBI images, because the noise images kind of look like blobs, right? And it ends up working really well, and we're really, really excited about this project as well. Okay, so with that, this is my summary. So M87 and Sagittarius A are both consistent with Kerr. I know I've just completely changed the lives of all of you by that completely unprecedented information that nobody expected. 10% bound in shadow diameter constrains deviations from Kerr. We are doing about 800 times better than what can be done in the solar system, and we're comparable to what can be done with gravitational waves. Primo achieves remarkably improved resolution and accuracy in the image. The first machine learning interferometric image reconstruction algorithm, as far as I know. There are other algorithms that will take the output of the other imaging algorithms and then like denoise them. But there, as far as I know, there's no other machine learning algorithm that actually is used to generate the image itself. And finally, the future is bright for the EHT. We have recent and upcoming observations with additional telescopes, higher bandwidth, and multiple frequencies. And with that, thank you all so much for your attention. And I'll take questions if you would like.
Yes, thank you so much. I was gonna come here and help you coordinate questions.
Stepping on toes. Oh, no.
I don't need this thing.
Oh, yes, you do need this.
Can I have two? Can I have two questions?
Yeah.
Thank you. This was amazing. Thank you very much. I had two questions. The first one about, so if I understood correctly, the EHT, so you simulate these black holes with gas and emission around them, and you forward model it to the visibilities in UV plane to report the final numbers that you give in the paper, right? With the confidence intervals and everything. Now, given that, do I expect to have different results with Primo if what I'm after is to constrain, for example, the radius of the shadow? Do I expect, if I have exactly the same simulations, do I expect to get different results if these are just forward models of the simulation?
So I think I agree with most of what you said, but I want to clarify one thing. So the other imaging results that we have published do not have any, they don't know anything about the simulations at all. So they're not related to the simulations at all. They are just these general purpose imaging algorithms where usually they try to maximize the entropy or they try to minimize the gradients. So there is no simulations there. And they're also blurring it with the Gaussian blurring kernel, where we're really kind of throwing away half of the power that we have at our longer baselines. What that means in practice is that by blurring it more, you actually bias the ring size a little bit. So if you blur a ring with a Gaussian, the radius will get slightly smaller, ever so slightly, but still not negligible. But also the fact that we have, you know, these additional features like these little blobs that we really don't trust, and the fact that we've blurred it out quite a bit, we do expect that the level of uncertainty will be different. So we expect that even though the actual ring size is consistent, the level of uncertainty we do expect to be different. I should say, though, I'm still in the process of running about 3,000 synthetic data sets with Primo, so I don't actually have the final results yet. So it might be that it's better by like a negligible amount, in which case, okay, fine, but we still have a much better constraint on the width of the ring, which really does constrain our theoretical uncertainty, actually. And so that even if the observational uncertainty is exactly the same, which again, I'm working on it, so I don't know, even if that's exactly the same, it should really help us constrain our theoretical uncertainty. It should also help us just compare simulations to the data in general. And also the fact that we have this really much deeper brightness depression should be really useful for tests of gravity in terms of having an event horizon or not.
So
Is that satisfying? Answer your question?
I think, just to make sure, so the radius, for example, is something that is measured from the reconstructed image and not from a forward model from the simulation to the UV plane?
Okay. So we do it in three ways. I think I understand your question about that. Okay, so the way that we constrain this diameter previously in previous CHT results is 3 different ways. One is we have this image, or we have hundreds of images, and we apply a feature extraction algorithm to that image. The second way is we try to fit this analytic crescent to the data, but you saw that there are biases with that, and so there's reasons why we should be a little careful and a little cautious. The final thing is we take each and every snapshot from the simulation, we rotate it, we scale it, and we try to compare it to the data. But that was my whole part about, like, you know, comparing different realizations of turbulence with each other. You know, if you're turbulent, if the morphology of the image is completely different because you have a different turbulent, you know, feature, there's no reason why the size that you get from that should necessarily be really robust. So, you know, we have these different analysis algorithms. What I always tell people is that I'm not necessarily trying to, like, completely replace all of those with Primo. I think it's really great that we have different ways to do this, right? And so we now have a 4th completely independent, completely orthogonal way of doing this that will add more confidence to what we're doing. It's still probably good that we do these general purpose imaging algorithms and things like that, because Primo is not completely model agnostic unless we use the noise basis that I showed you at the very end. But yeah, does that help a little bit? Okay, great. I'm gonna let you pick.
Right here.
Great talk, Leah. Thanks.
Thank you.
So yeah, this blob that shows up in the Primo reconstruction.
You mean the little tail?
Yeah, the little
Yeah.
tail. Yeah. Like, so you see this in a lot of these
Mhm.
movies and stuff too. Like, what could that be? Is it like an asymmetry in the disc, or is it like a function of viewing angle?
Are
And like you
we-
alluded to, like, if you can see it moving, like, you know, what kind of physics can you get at if it is real?
Please hold. Where do I have it? Do I not have it? Okay, hold on. I do have it. It's just hidden. Just give me 1 second. So sorry. You can check your emails as I do this really quickly. Aha. Okay. So we observe on 4 different days. The baseline coverage is different on these different days. In particular, April 10th is absolutely terrible. We have like 7 scans as opposed to like 25 on the other days. So just ignore April 10th because we really don't know what's going on. April 5th is also not great, but April 6th and 11th are pretty reasonable. And so here we have a, you know, this is like the best fit image, right? It has this little tail. In both of these, you can almost see that there's a little tail, but we're really not sure, right? And this is a few days before, right? So you could almost argue that, oh, look, it looks like it moved ever so slightly. Yeah, I'm not going to make that claim, right? Like, maybe in the future, I think we totally could, right? In 2022, I'm super excited for 2022 data. It's going to be amazing. And I think we could absolutely constrain these kinds of things. And then, you know, there's this whole other thing about, like, you know, can you constrain the spin if you can constrain how the rate at which these things move? So anyway, so part of your question was, what is this? Is this being recorded?
Yes, it is, but we're not going to post it on the.
It won't be on YouTube?
Yeah, it will not.
Okay. So one of my close collaborators is Ramesh Narayan at Harvard, and I showed him this image, and he looks at this and he goes, that's the jet. That's the edge of the jet. And that would be amazing if that were true. I am not comfortable claiming that. I look at this and I think that the highest likelihood thing is that it's just one of these little wispy features that's moving around. And I am hopeful that we will be able to really detect that and really make, like, effectively a movie of these little wispy features rotating around, which would be super exciting and super wonderful. So, you know, give me like a year or 2.
Cool,
So
thanks.
hopefully soon.
I think we have time for one more question.
Yeah, this one's actually from Josh Simon, who's online.
Wonderful.
For M87, is there variability expected between 2017 and 2023?
Yes. So even at this level, right, like this level of change, we do expect to see a little bit of, like, that is possible. right, this level of variability. Between the observations that we did in 2017 and what we're seeing now in 2023, like the realization of the turbulence could be completely different. We think that because of the orientation angle of the spin axis of the black hole, based on the fact that we observe this really large scale jet at longer radio frequencies, we expect that the kind of the southern half will be brighter more frequently than any other part, right? So like statistically, there is this variability and there's all this different, turbulence that can kind of move around these bright spots. But statistically, given the location of the spin axis, which is kind of like that direction, we think that it is higher likelihood that we will see bright spots being on the bottom half of the ring. So I would not expect that the ring size would change, because then the mass of the black hole is changed by a really crazy amount in a really short amount of time. These are low accretion rate sources. That's completely ruled out. If something like that happens, it means that we've messed up effectively, right? That there's some uncertainty that we've not calculated, or that, something was some error that we didn't take into account. So the ring size really shouldn't change. The bright things might move a bit. Yeah.
Great. Thank you so much. Before we thank our speaker for one more time, I'd like to encourage everyone, there are still spots on Leah's calendar or schedule for the day if you'd like to meet with her and discuss all of this fabulous images and the tests that she's done more. But with that, please, let's thank our speaker one more time.